What if the biggest bottleneck in the artificial intelligence revolution isn't a lack of computing power, but a flaw in how we organize knowledge itself? Imagine a world where our most advanced algorithms stumble not on complex calculations, but on the silent, invisible weight of unstructured data. Welcome to a deep dive into the intelligence revolution of 2026. Today, we are unpacking a series of groundbreaking studies that challenge our assumptions about how machines learn, reason, and evolve. We will explore why static prompts fail to capture dynamic reality, how new mathematical frameworks are slashing communication costs, and what these shifts mean for the future of science and society. Stay until the end because the final insight reveals a hidden failure mode in self-evolving agents that could redefine how we trust artificial intelligence. For years, the prevailing belief was that we could simply inject static skill files into large language models to make them better data scientists. The assumption was that automating domain knowledge through fixed prompts would scale effortlessly, replacing the need for human curation. However, a massive ablation study spanning over 7,000 runs across 56 tasks has shattered this illusion. It turns out that these static skill files provide no reliable performance improvement over simple task-only prompting. This is a pivotal moment. It forces us to realize that pouring more static knowledge into a system does not automatically yield wisdom. Instead, it highlights a critical misallocation of resources, suggesting that the path forward lies not in rigid injection, but in dynamic, context-aware orchestration. If we continue to rely on static structures, we risk building systems that are brittle, unable to adapt to the fluid nuances of real-world workflows. But if static knowledge hits a wall, where does the breakthrough lie? The answer emerges from a trio of transformative discoveries reshaping the landscape. First, consider the challenge of communication in distributed training. As models grow, the volume of gradient data exchanged between processors becomes a choking hazard. Enter the GIFT framework, a geometry-informed approach that transforms gradients into near-isotropic coordinates before quantization. By doing so, it reduces communication volume by a staggering 75% while preserving model fidelity. Think of it like folding a massive, unwieldy map into a compact pocket guide. The information remains intact, but it becomes effortless to carry and share. This solves the critical trade-off between speed and accuracy, unblocking faster scaling on superchip clusters. Simultaneously, we are witnessing a leap in how agents handle memory and context. The traditional bottleneck of linear recurrent neural networks, which struggle to recall long sequences, has been overcome by sparse delta memory. This innovation scales the hidden state to millions of slots via sparse addressing, maintaining a constant computational cost regardless of how much data is processed. It is akin to giving a librarian an infinite shelf space that never gets cluttered, allowing them to instantly retrieve any book from history without slowing down. This bridges the gap between efficient linear models and the long context recall needed for complex tasks, enabling agents to process arbitrarily long contexts with a minimal compute footprint. Furthermore, the narrative of success is being rewritten through the lens of determinism. In the realm of tool-using agents, a silent failure mode known as policy violation has long plagued performance. Researchers have demonstrated that implementing deterministic pre-execution gates can block these invalid actions before they occur. This simple structural change boosts success rates from roughly 30 to 42%. It shifts the focus from hoping for probabilistic success to engineering deterministic guarantees, ensuring that syntactically valid but logically forbidden calls are stopped in their tracks. Together, these findings paint a picture of an AI ecosystem, maturing from brute force computation into elegant, efficient, and reliable reasoning. So, what does this confluence of insights mean for humanity? We are standing at the threshold of a new era, where artificial intelligence moves beyond merely mimicking human output to genuinely augmenting human capability. By resolving the trade-offs between communication efficiency, memory scalability, and policy safety, we are unlocking the potential for AI to tackle problems previously deemed too complex or resource-intensive. This evolution promises to accelerate scientific discovery, from translating whole-body medical images with unprecedented accuracy to automating the analysis of single-cell trajectories without relying on expert heuristic tuning. It suggests a future where AI acts not as a replacement for human judgment, but as a powerful partner that handles the heavy lifting of data processing, allowing us to focus on creativity, strategy, and ethical governance. The shift from static to dynamic, from dense to sparse, and from probabilistic to deterministic marks the true coming of age for the intelligence revolution. As we close, reflect on how these subtle shifts in framework and perspective are quietly rebuilding the foundation of our digital world. The move away from static skills toward dynamic orchestration, combined with breakthroughs in efficiency and memory, is paving the way for AI systems that are not just smarter, but more trustworthy and adaptable. If you found these insights as fascinating as we did, please like this video, subscribe to our channel, and comment your thoughts on which of these breakthroughs excites you the most. And stay tuned for our next episode, where we will explore how these self-evolving agents might just teach us something new about our own cognitive biases.